Okay, let's try to formulate it first. We defined the decision variables. X1 is equal to number of pounds of brand 1. Alright, and X2 is number of pounds of brand 2. Please note that pounds can be written with LBS. Pounds. LB is also used for writing pounds.
Dr. Arif, do we have to worry about conversion?
Okay. Now let me write down the formulation first, and then we will see that whether we have to do the conversion or not. We have to find the variables in terms of pounds of gram. So first of all, we will write down the cost. Okay, minimize the cost. Minimize, objective function is to write down minimize cost, and let's say Z is equal to, we have 2 cents per pound. So this is given in per pound. So 2 into number of pounds will give us the cost in cents, right? 2x1 plus 3x2. 2 is in cents per pound. Multiply with pounds. Pounds cancel. We will left with cents. So the cost will be in cents. Alright. Then subject to, we have, clearly we can see 3 constraints are there. Constraint A, B and C. For ingredient A, B and C, we have 3 constraints. Right? And it says that in brand 1, 5 ounces of ingredient A is there per pound. 5 ounces per pound. When you multiply with X1, which is also in pound, okay, this pounds cancels, and we have left with ounces. So this one 5x1, okay, plus 10x2, all right, should be greater or equal to 90 ounces. This is the requirement. It is also the right hand side of the constraint is also in ounces. This one will be in ounces, this one is in ounces, and also this one is in ounces. If the right hand side is given in pound, we have to convert the right hand side into ounces, or we can convert this into pounds by dividing it by 16, and this can be converted into pounds. So the both ways is possible. Now we don't have to convert these constraints into pounds because these are all in ounces. Okay, the right hand side and the left hand side are both in ounces. Okay, so this is 5x1 plus 10x2 greater or equal to 90. The next constraint is 4x1. I should remove this ounces now. We can write it down. 5x1 plus 10x2 greater or equal to 90. Then we have 4x1 plus 3x2 greater or equal to 48. And the last constraint is 0.5x1 greater or equal to 1.5. And to complete the formulation, we should have non-negativity constraint, that x1 and x2 both should be greater or equal to 0. x1, x2 should be greater or equal to 0. And of course, when we are solving it with the graphic approach, we will be working on the first quadrant, where x1 and x2 both are positive. Good. So once we have formulated them, we then draw the constraints and solve. I think we can just look at it. I hope that you can solve these by graphing them. It's a straight line graph. Straight line equations are there. Identify the feasible region and then identify what are the corner points, work out the cost at each corner point, and the one which gives the minimum is your solution, optimal solution. Let's look at that. We have this formulation here. Okay, you have already done it. This is the feasible region here, and the corner points are A, B, and C. Please note this third constraint. This is drawn here like this one, 0.5 x1 greater or equal to 1.5, 0.5 greater or equal to x1 greater or equal to 1.5, which we can say that x1, if we make it equality, x1 is equal to 3. Alright, how to draw this? Just straight line on x1. x1, x2, if this is 3, then this is your constraint. It doesn't go to the negative side, alright, and it is just 3. Clear? So this is the ingredient C constraint here drawn, and these are the two constraints. We have 3 corner points. Sometimes, let me tell you that some students try to work out, they don't draw the graph properly, and instead of having this point A as in the feasible region, they might come up with this point in the feasible region. Okay, solving, when they solve this with this, they come out with this corner point. Okay, this is the normal mistakes the students do. They don't work out properly on the graph, and sometimes the point is not in the feasible region and they show it in the feasible region. And that's it. I mean, you work out these coordinates of these points A, B, and C, and the one which gives the minimum is your optimal. Okay, this is the working out of that, and the cost at point B is the minimum. Okay, this is point B here, and this is the isocost line drawn, and if you move towards the origin, the last point hit, this is the parallel line, the last point hit is this point. X1 is equal to 8.4 and X2 is equal to 4.8. This is your optimal. Any questions? The next topic is some special cases with irregular types of linear programming problems or special cases. These special cases are multiple optimal solutions, infeasible solution, and unbounded solution. Okay, let's see what are these special cases. Here, you see the same problem we have seen earlier, that Beaver Creek pottery case in the last lecture. Same problem, except that there in the coefficient in the profit objective function, we had 50 over here, not 30. Let's say it is 30 now, and one of the constraints you can see over here is 4x1, oh it's mistake here, 4x1 plus 3x2 less or equal to 120. And this one is 40x1 plus 30x2. Please note, they have the same slope. If you divide by 10 here, this will become 4 and this will become 3. And this is also 4 and 3. Okay, so these two isoprofit line and this constraint has same slope. Now if you draw the feasible region, and you see over here the point from B to C and the isoprofit line, when you move away from the origin, this isoprofit line, if you move away from the origin, the last point hit will be point B and also C, because this is exactly parallel to BC. Okay, exactly parallel to this constraint. So it will be sitting on the top of it, and these two corner points will have the same optimal solution. In fact, because it is an isoprofit line, any point on this infinite number of points, all will give the same answer, same optimal point. So in nutshell, what we can say is this, that if the objective function slope and one of the active constraint, not redundant constraint, active constraint, has the same slope as the objective function slope, then we will have multiple optimal solutions. Please note also, I can ask this question in your final exam just by asking what is the condition for optimality for multiple optimal solutions, and you just have to write it down. Or I can ask you this question in terms of objective type questions, that if one of the constraint and the objective function has the same slope, then we have 3 or 4 options there. Is it infeasible solution? Is it multiple optimal solution? Is it redundant constraint? Is it this, that, unbounded solution? You have to select the right one. Okay? We are not restricted to give you only multiple choice questions from that 2 sets we have provided to you. Okay, the 2 sets of questions, the items, test items. We will ask from this portion also multiple choice or true false questions. So you should be ready and understand the things. Clear? Okay. Now you see over here point P, x1 is equal to 24, x2 is equal to 8, z is equal to 1200, and x1 is equal to 30 at point C, and x2 is equal to 0, and z is equal to 1200 again. Same optimal solution is there. Clear? This is advantages for management point of view. They can make 24 bowls and 8 mugs, or they can make 30 bowls and 0 mug, and they will still have the same profit. They have this advantage, and in fact they can make any combination from here to there. Okay, because this is over is multiple optimals are there. This is actually isoprofit line. Any point will give the same optimal. So from management point of view, it's good. Okay, they have a flexibility. Now let's look at another irregular case in which we have infeasible solution. You see over here, if we draw these constraints, we have no unique feasible region. There is no unique feasible region. We have one constraint, for example, this one says 4x1 plus 2x2 less or equal to 8. This constraint is saying this is the feasible region. This x1 greater or equal to 4 is saying this side is the feasible region, and x2 greater or equal to 6 is saying this side is the feasible region. Okay, if these two constraints are there, the feasible region will be this one. But there is a third constraint, this one, which is saying the feasible region is on this side. So there is a conflict. There is no unique feasible region. And because of this conflict, there is no solution. It is called infeasibility. This may happen because someone has done a mistake in formulation. Okay, if you make a mistake in formulation, in the signs, etc., of the constraints greater or equal to, less than or equal to, we made a mistake, then it can happen. The solution may be infeasible. And third irregular case is unbounded solution. Unbounded problems occurs only in maximization problems. Please note, unbounded problems occur only in maximization problems. Okay, if I ask question, multiple choice question or true or false question, that unbounded problem occurs in minimization problem, true or false, so you will say false because it occurs only in maximization problems. Okay, so you can expect such kind of questions in your final exam. Clear? So you should know that the unboundedness occurs in maximization problem. Here it is, unboundedness is, if you draw these two constraints, x1 greater or equal to 4, this is the feasible region, and x2 less or equal to 2 is, this is the feasible region. But there is, since this is your isoprofit line, you can draw isoprofit line and increase it to infinity. There is no bounded thing. You can make your profit to infinity. It means some constraint is missing. Some constraint is missing. Unboundedness is there. The region is not bounded. Okay, if the region is not bounded, of course, you can make your profit to infinity. And this kind of problem occurs only in maximization problems, not in minimization problem. You can increase your profit to infinity. You can move your isoprofit line away, and there is no boundedness. Clear? Okay. You can ask question even though it is recorded. You still can ask questions if there is some doubts. If there are some doubts, please don't think that recording is going on, so we should not ask question. Okay. Okay. Some books give these characteristics before, and then they start giving the examples. Here in this book, it's just opposite. They give the examples, and now they are telling what are the characteristics of linear programming problems. So I just didn't change the slides, put them in front, or later I kept it like that. The characteristics of linear programming problems are a decision among alternative courses of action. There will be alternative courses of action. This is one of the characteristics of linear programming. Another is the decision is represented in the model by decision variables, and there will be objective function and constraints, and both objective function and constraints would be linear. Mathematical linear relationships will be there. These are the characteristics of linear programming problems. There will be alternative courses of actions. There will be decision variables to decide about, and then there will be objective functions and constraints, and these will be all linear with mathematical linear relationships. Another property of linear programming models is proportionality. And the proportionality, additivity, divisibility, and certainty, these are the properties of LP models. What are these? Proportionality is the rate of change of the objective function, and constraint equation is constant. If in this we had this example, x1 was number of bowls, x2 number of mugs, and we were maximizing 40x1 plus 50x2 subject to, we had two constraints, x1 plus 2x2 greater or equal to 40, and 4x1 plus 3x2 greater or equal to 120. This was labor constraint, and this was material constraint, plate. The proportionality says that if you make, let's say, if you make one bowl, okay, you will have a profit of $40. If you make 10 bowls, it just multiply by 10. So this is proportionality. Similarly, the proportionality exists in the constraints as well. If 1 hour of labor is used in making one bowl, if we are making 10 bowls, 10 labor hours will be used. Here 2 hours are used for making one mug. If we are making 10 mugs, 20 hours of labor will be used. So this is proportionality. Okay, this is a function of linearity. The second property is additivity. Terms in the objective function and constraint equation must be additive. Again, you can see it is a linearity property. If you make one bowl and one mug, you will have 40 plus 5, 50, 90. 10, 10, just add them. So additivity is there in the objective function. The same goes here. If you make one mug, one bowl and one mug, you will use 3 hours. So this is simply additivity is there. Alright, linearity is there. This is the property of additivity. Terms in the objective function and constraint equation must be additive. Divisibility. This property is that we accept the solution in linear programming in decimal numbers. So if our solution says that x1 is equal to 2.3 bowls and x2 is equal to 9.4 mugs, if this is our optimal solution, we will accept that. Although these are not integers, the decimal numbers are there. We cannot make 2.3 bowls and 9.4 mugs, but we accept this solution in linear programming. This is called divisibility. The divisibility is the property of linear programming. If we want the solution strictly to be integer, then there is one branch, special branch of linear programming called integer programming. All right, we in this linear programming we accept decimal solutions. Decision variable can take any fractional value and are therefore continuous as opposed to integer in nature. This is called divisibility. Certainty. Certainty is that value of the model parameters are assumed to be known with certainty. There is non-probabilistic. As you can see over here, these numbers here 40, 50, 1, 2, 4, 3, these parameters, these are considered constant when we are solving this LP problem. So this is certainty. We are certain that this one bowl will bring $40 profit to us. Or if we make one bowl, 1 hour labor hour will be used and 4 pounds of clay will be used. This is certainty. Now, since this is certainty and the real world is more probabilistic in nature, the labor cost may increase or the clay price may go up or down. The variations will be there in the profits, the variation will be there in the cost, the availability. We have a new machine which can cut these numbers. All right. These are also called technological coefficients. That's why they are called technological coefficients. The constraints parameters are called technological coefficients. They may change. So for that purpose, we have to do sensitivity analysis. What if analysis? What if this profit changes? What if these values changes? Okay. For linear programming, because linear programming, the certainty assumption is there, it is not probabilistic, but the real nature is probabilistic in nature. The things are not constant all the time, so we can do sensitivity analysis. In fact, the next lecture will be related to sensitivity analysis. Okay? Okay, now there is a problem here. You just are asked to formulate. Please formulate this problem. Now the rest of the lecture is finished. Basically now some exercises are there. Okay, so please write down the objective function, constraints, identify the variables, etc.